we're now looking at this thing called the second derivative. And what I said before was, I guess you could say, it measures how the first derivative changes, because a derivative measures a rate of change. Well, we have a name for that, and we call that concavity. Right? So the second derivative measures the change in the slope, and that's concavity. So if you start with a negative slope, and then it gets more and more positive, then you have a concave up parabola. Because if you have a look at that, it starts with negative, and as you go down, it's getting shallower, 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 0, and then it becomes positive and starts getting steeper and steeper. And so it's got a positive change because it's getting more positive. So if the second derivative is positive, we know we'll end up with a concave up shape. Well, consequently, if we end up with one that's negative, it must be the opposite case. It must start off very steep positive, and then it's getting more negative as we go along. So it goes to naught, then to negative, and so we end up with a concave down parabola. If it's equal to 0, so if it has no concavity, then that's what we call a point of inflection. A point of inflection is where it changes concavity. So if it's 0, because before you can move from positive to negative, you must pass through 0. You can't just jump over it. So that's where the change would happen, when it's equal to 0. Now this gives us a little bit of an advantage, because you remember the other day when we were sort of investigating the stationary point, we had to use a table of values. But if we now combine this idea with stationary points, then it's a lot quicker. Because if I know it's a stationary point, but I know it's concave up, what type of stationary point must I have? A minimum. Thank you. Someone said the word I was looking for. Because if it's concave up, my head's the stationary point, by the way, if you hadn't worked that one out. Here I am down the bottom. But if I was concave down, I'm up the top. So it's a maximum. So that saves a lot of time. Mind you, if it was a difficult function to differentiate, and at the moment we're not really dealing with difficult ones because they're mainly polynomials, but later on we might get more complicated functions, then possibly drawing the table of values and just investigating the first derivative is going to be a better way to go. So it all just depends on how difficult the second derivative is to find. So alright, this time we're just going to look at the second derivative, and we're going to get an idea of what this cubic looks like. So differentiate it once, get the first derivative. Differentiate it twice, get the second derivative. Now remember I said when it equals 0, that's where it'll change from concave up to concave down. So what I'm going to do is I'm going to find when it's greater than 0, and that's greater than minus 5/3. Now from that I can logically conclude the others. It must be equal to 0 at negative 5/3. And then when it's less than minus 5/3, it must be less than 0. So what I now know is minus 5/3, that's where it's going to change. On the right hand side of it, so when it's greater than that, the curve is going to be concave up. And on the left hand side, it'll be concave down. Something like that. Again, a very rough sketch. If I wanted to find those turning points exactly, I could use the first derivative. The y-intercept, how close did I get? What was it? Y-intercept should be 2, so okay, at least I made it positive. X-intercepts, I'd have to solve that. But I say, it's a very rough sketch. At least we've got an idea of what the shape looks like. So let's look at those turning points in a little bit more detail. So let's say, all those turning points are in fact stationary points. I mean, that's how we locate them. Remember, I was saying, concave up, here I am, down the bottom. Minimum turning point, concave down, up the top, maximum turning point. So if I now want to find the turning points and then go and classify them, I'll need both tools. I'll need the first derivative and I'll need the second derivative as well. Now my first derivative will locate them for me. So the first thing I do is locate the stationary points. Solving that equation, there we go, I've got two possibilities. Now yes, I could draw up the table of values, But now I can check concavity instead, and that's going to be a lot quicker. When x equals -1, sub that into the second derivative, I get -4. Well, the actual number I'm not interested in. I'm really just interested, is it positive, is it negative? That's a negative number, so that tells me concave down, maximum turning point. Let's check the other one. Sub that in, I get +4, so it's concave up, minimum turning point. Right, let's talk about these inflection points. So that point where it changes concavity, where it moves from concave up to concave down, or vice versa. Yeah. Just like with our first derivative, when we wanted to see what type of turning point it was, we tested either side of the point. Well, we can do that with concavity. We can find the possible inflection point, test either side to see if it does change concavity or not. Yeah. So let's find any inflection, well, points, I don't know, there might be one, there might be none, there might be several. Mind you, it's a cubic. Therefore, how many should I have? Hang on, what did I hear over here? One. There's your basic cubic right there, y equals x cubed. It'll change concavity once. And in fact, all cubics will change concavity once. So I'm expecting one solution. Now, the reason for that, when you think about it, if I've got a cubic, differentiate it once, I'm going to get a quadratic. We know quadratics, 2 solutions. Differentiate it twice, I end up with a linear function. Linear functions have 1 solution. So my possibility, now see this first word here? Possible. That's really important. Just because the second derivative equals 0 does not mean that it is an inflection point. It's just a possibility. That's why we need to test it. So let's find the possibility. The possibility is -1/2. Let's draw up a table of values. Okay, so -1/2, we just found that it had no concavity. So really, this is just the same as when we were testing stationary points. I need to pick one on the left-hand side or the negative side, pick one on the right-hand side or the positive side. So on the left-hand side, I've chosen -1. Sub that into the second derivative, make sure you get the right derivative, and we get -12, concave down. Now, if this is an inflection point, on the other side, I should be concave up. Let's substitute in, I've substituted in 0, nice easy number to work with. I get +12, concave up. Yes, there is a change in concavity. Now that statement there is crucial in your solution. Because when they're marking, they want to see that you understand what an inflection point is. So you've made the conclusion, yes, there is a change in concavity, so you understand that to mean there's a point of inflection. So from there we can deduce -1/2, 3 is a point of inflection. The very special type of inflection point, which is on our basic cubic, what we call the horizontal point of inflection. So it's both a point of inflection, but it's also a stationary point. So it would have the conditions, the first derivative would equal 0, because it has a horizontal tangent. The second derivative would equal 0. Yes, it is a possible inflection point. And, what? Third derivative does not equal 0. Now I'm going to let you in on a little secret. It's not in your textbooks, okay? Think about it logically. What is an inflection point? What did I say it is? Anyone? Change. What does the derivative measure? So if I want to measure the change in concavity or the change in the second derivative, what would it be logical to do? Right, differentiate it, because the derivative of the second derivative will measure the change in the second derivative. But what do I want the answer to be? If there is a change in the second derivative, what are you expecting in the third derivative? Or more to the point, what are you not expecting? Because if it was 0, then it'd be saying there is no change in the second derivative. Any other number, and there is a change in the second derivative. That's why I've put there, the third derivative does not equal to 0. So an alternative way of doing it, yes, we still locate our possible points of inflection. Second derivative equals 0. This is the actual rule. The actual rule is, if the first non-zero derivative, if it's even, then it's not going to be a point of inflection. It's probably going to be a turning point. And we know that one is over there. So minus x to the 6. Now obviously, finding 6 derivatives, it might be easier just to use the second derivative and test either side of the point. Most of the functions you're going to look at, the third derivative will work fine. The ones that it won't work with are going to be basic functions like, y equals x cubed. But you know what that looks like anyway. So let's do that same example. But now I'll find the third derivative. Third derivative turns out to be a constant 24. So how would I write my solution down? I would have found the possible inflection point at minus a half. And I'm going to say at x equals minus a half, the third derivative is 24. Well, that's not equal to 0. Therefore, there is a change in concavity, because we have a value to that third derivative. Well, if there's a change in concavity, it's a point of inflection. Now, a word of warning to you. If you're going to use this method, make sure you use this. Because some of the other teachers think this is a little bit dodgy. This weird mathematics, magic method. It's not in the textbook. How can we use it? It's not in the textbook. But this is maths. I mean, you think about it logically. Derivatives measure change. There's no illegal maths we're doing here. It is perfectly fine. Just make sure you explain your logic on this one. So, I know it's not equal to 0. Therefore, I know there's a change in concavity. Got to be an inflection point. Okay, that's enough from me.